Hello, this is the Stellantis Battery Management System team, and we're part of the Wireless Communications Enterprise. We'll be talking about our members, our objectives, the process we took to complete them, our conclusion, and the future considerations of the project. My name is Stephen Gilman. I'm the team lead, and I'm part of the cell balancing subteam.
I'm Benjamin Sawyer, and I'm part of the cell balancing team.
I'm Alex Stockman, and I'm part of the cell balancing team.
I'm Jared Bush, and I'm part of the wireless module connection team.
Our advisor is Cischke. We're part of the EC department, and our sponsor is Stellantis, who you may know as FCA or Chrysler.
So for the objectives, our timeline was the fall of 2021 into spring of 2022. We're picking back up from the 2020-2021 Stellantis project. We are reestablishing the project after a complete turnover from last year. Main goals were adding battery cell balancing capabilities for increasing battery pack efficiency and add battery module hot swapping capabilities for the serviceability in the field. We've got module to microcontrollers to measure cell voltages and balance them, as well as the BMS can pull info from those module microcontrollers.
Our process is as follows. In fall of 2021, we onboarded the new team, which was the majority of us here, and we designed preliminary cell balancing solutions. In the spring of 2022, we got into manufacturing and testing our cell balancing circuit and iterated our design for robustness and ease of use. We've also been working on designing a wireless communication protocol that handles new and disconnected modules and allows for specific module voltage requests.
Our process continues by using a differential op-amp method for measuring voltages. On top of that, we use a microcontroller activated transistors to drain individual cells. The circuit board manufactured in Plexus Makerspace Lab, which our members were in charge of. We have a battery management system, which is the Raspberry Pi. The microcontrollers is the Arduino Mega 2560, and the communication is processed through the XB 802.15.4. On top of that, we have a dictionary of device objects which handles the communication from batteries to the Raspberry Pi. The parameters are defined on the device communication payload by relaying important information about the battery statuses.
So a little bit on more detail on how this works. Basically, the individual batteries are inside of a larger module. So each cell is separate inside the module, and then multiple modules could be connected to a single payload, which could be a vehicle, like an electronic vehicle like you see here. Those are wired through a circuit board to an Arduino, which communicates to the Raspberry Pi via a pair of XB units. And the payload communication that was referenced previously is what handles this. The protocol was defined by the team, and it's able to parse information to the user on the screen connected to the Raspberry Pi.
So in conclusion, what we've done in this semester and in the fall semester has been to design and implement voltage measuring and cell balancing circuitry for battery pack modules in vehicles. And we're able to relay these commands and this information wirelessly. So far, right now, we're working on integrating everything together instead of having it separate, but we're combining it right now. In the future, what our sponsor has desired is to migrate project work to high voltage battery modules, so in excess of 40 volts, which means we would have to have see if the same concept will work, but then redesign and reanalyze if our components in our design would work for a higher voltage load. Thank you.
Our testing process consists of two parts. This part is with the Raspberry Pi side, the main controller. This is the hardware that will be communicating with the modules to ask for what voltages are currently being read, or to send commands to specifically each module to request information from that module. How we can test this out is with a breadboard with the Arduino, or with the Raspberry Pi right here, and our wireless communication module, the XB, connected to it via breadboard. What we do is we open up a Python editor and run our program to input values saying, do we want voltage 1, do we want device 1, so anything like that. Then we can see what voltages we're getting. The second part of our testing setup is on the battery module side. Each battery module contains a Arduino with the wireless communication XB with one of our homegrown boards, as well as the battery module. The testing processes we usually have are with a multimeter to detect and probe each voltage at every pin that we want to look at. These are cell balance outputs from the Arduino to this board. Right now we're testing that by actually connecting it instead to its own circuit of LEDs and resistors, so we can tell which one should be on and off without actually draining these batteries. We can test the wireless communication as well by the Raspberry Pi script, but if we wanted to not use wireless communication, what we can usually do is plug into our laptops on the Arduino IDE and print out the serial and read it from the serial terminal there.
So trying to do some CAD things. So right now, well, yes, these are just a bunch of squares and rectangles. What they're supposed to do is they're supposed to hold our lasers down so they don't overlap.
This circuit board controls the different powers of the lasers. So it connects to an Arduino, and then it takes the different signals from the Arduino and sends it to the lasers. So these are the lasers that we're going to shine through this prism. Byron's working on the galvos right now, but it would go here to control the direction of the lasers.
Cool. What's that thing?
This is the motor control for the different mirrors on the galvos. They would connect into the different motors using these.
Here's our process for making images for our laser show. First, we take a raster format like a JPEG or PNG file, use Inkscape or similar software to trace it into a vector format image. Then we run that through a homemade Python script of ours that converts it to G-code, which includes the color data and X and Y coordinates in a human readable form. And then from there, we run it through another Python script that converts it into Arduino code, which consists of X and Y coordinates and color codes, but in a hex format that our main program can read.